Hello, this is a video for Math 2-3 explaining matrices. This is part 4 of working with variables in matrices. There are some very familiar, easy things that we can start with. The good old familiar x plus 2 equals 7, where you subtract 2 from both sides, giving us x equals 5. We're going to use that technique inside a matrix. It's pretty easy, right? This one, you subtract 5 from both sides, and we end up with cancellation there. So negative x equals negative 8, which means that positive x must equal positive 8, dealing with negatives. And then the easy undoing multiplication technique. Divide both sides by the coefficient of a on this side, leads to cancellation, so a equals 5. All that easy stuff is going to be used along with matrices. Let's look at this. It looks much more complicated than it is, because we know that taking this whole matrix and adding it to this whole matrix just gives us this matrix. So that means that each individual part that gets added together to get this result just gives us one simple equation. X plus 1 equals 10. So of course, x equals 9. And that gives us the number that goes in here. Subtraction works about the same way. We just look at the parts, the elements that we are concerned with, and we just show that 4 minus a equals negative 3. Subtract 4 from both sides. So negative a equals negative 7, which tells us that positive a must equal positive 7. And that value of a, 7, is what would go in here. It works very similar with scalar multiplication. First, notice that there's 2 variables in here, so we're going to have to do 2 separate equations to solve for them, because those variables will probably have different values. First though, this right here, the 2 times the matrices, similar to the way that we work with a set of parentheses, this would usually be just written as 2 next to the matrix P, Q, 8, 1 equals the result matrix of 12, 6, 16, and 2. Notice that we know that this equation works because 2 times 8 is 16 and 2 times 1, of course, is 2. So we've got 2 separate equations that quickly give us 2p equals 12, meaning that p equals 6 by dividing both sides by 2, and 2 times q equals 6, so q must equal 3. And that gives us the answers, the results that go in for p and for q. In this example, we've got a variable standing for an entire matrix. Notice that this is a capital A. Generally in matrix manipulation of any kind, we use capital letters to stand for an entire matrix. Doesn't matter what the size is or what the contents are. If you see a capital letter in these, you know you're looking for an entire matrix. So let's turn that into an equation here. And since we know that this one here is a 2 by 2, and whatever's added to it gives us the result of a 2 by 2, since with matrix addition, the 2 matrices have to be exactly the same size, so our result matrix here would have to be a 2 by 2 also. So we've got a 2 by 2 plus 1, 2, 3, 4 equals 1, 1, 3, 5. And instead of going through and writing out 4 separate equations for this to deal with 4 separate variables here, each of the variables representing one of the elements of the matrix, I'm just going to do it the quick way and think, what plus 1 equals 1? Well, 0. What plus 2 equals 1? How about negative 1? What plus 3 equals 3? That's 0. And of course, that would make this 1. So here we've got capital A, means that we're standing for an entire matrix. We know it's a 2 by 2, so it's the matrix 0, negative 1, 0, positive 1. It's very similar with scalar multiplication. Here, capital B must stand for an entire matrix. And since with scalar multiplication, the result matrix is the same as the matrix over here, we know that B is going to be a 2 by 2 in this case as well. I'm going to do it a little bit different here. Generally what we would do is divide both sides by 3, but instead of that, since I want to avoid multiplication, I'm going to multiply both sides by the inverse of 3, also known as the reciprocal of 3, which would mean that we multiply this side by 1/3 as well. 1/3, which is the reciprocal, or we often call it the inverse of 3, times this matrix, will give us this. Because 1/3 times 3, that cancels out. 3 divided by 3, or 1/3 of 3, that's just 1. So this gives us, quickly, 4, 8, 1, 3. So now we can say that B, the matrix B, equals that, 4, 8, 1, 3. To sum up, variables can stand for elements of a matrix or for the whole matrix. The variables can be solved for using familiar rules of algebra, like undoing addition, undoing subtraction, undoing multiplication, etc. Generally, we use lowercase letters to stand for elements inside a matrix, or sometimes for the scalar outside that's multiplied. Capital letters usually stand for entire matrices. Solving for a whole matrix involves solving for each of the elements inside the matrix. And that's done.